Okay, so by request, I'm going to do a Coulombs Law question. And on this question, it's a two-dimensional forces question. We've got four charges. They're all positive. They each have a value of 1 microcoulomb. And they're all 5 centimeters apart. Well, they can't all be 5 centimeters apart from each other. They're arranged in corners of a square, and the side length of the square is 5 centimeters. And the question is, if I have four charges of equal value, all arranged on the corners of a square, what is the force that one charge is going to experience? So I'm going to label these four charges. So I'll call this one charge 1, 2, 3, and 4. And then I'm going to choose one of them to find the force on. So I'm going to choose charge 2. So we're going to look at this charge, find all the electrostatic forces that act upon it, add them together, and that's going to be the net force on this particular charge. If I'm to draw a free body diagram of that charge, so this is charge 2. Notice we have all positive charges, and there's a force of repulsion. These positive charges all push each other apart. So charge 2 is going to be pushed this way from charge 1. So I'm going to call this force F1. Let me draw it on here. So if this is charge 2, that's force 1. Because charge 1 will push this way on charge 2. Likewise, this is the force from this one here. So I'm going to call that F3. That's the force on charge 2 from charge 3. And finally, force 4, it's going to push this way. You can see that, right? This is charge 4, and it's pushing on charge 2. That repulsion is going to go this way. Notice this is a greater distance, so I drew it here as a shorter arrow. Why would it be a shorter arrow? Because the magnitude of the force due to electrostatic charge is inversely proportional to the square of the distance. What that really means is as we get farther away, that force gets weaker. So I'm trying to illustrate that issue by putting a shorter arrow on from F4. So all I need to do now is find the magnitude of these forces. I know the angles of them. These are perpendicular to one another. So this is, let's say, forward. And this one here is right. And this one here is forward and then 45 degrees to the right. So I want to find their magnitudes, and then I want to add them all together. Okay, to find the magnitudes of force 1 and force 3, and can you see the symmetry of this situation? The force coming from charge 3 and the force coming from charge 1 are going to be the same in magnitude. They're the same distance away, and the charges have the same value. So the magnitude of force 1 is equal to the magnitude of force 3. They do have different directions, but the same magnitude. And that is K Q1 Q2 over R squared. And I just need these values. If you're working in SI units, that is, charge is measured in coulombs and distances are measured in meters, then the K value is 9 times 10 to the exponent 9. So I'll list the various things out here. K is 9 times 10 to the exponent 9. Q1 and Q2 have values of, so Q1 is equal to Q2, and in this question we're given, it's all 1 microcoulomb. Which is 1 times 10 to the negative 6 coulombs. And R, that distance, was 5 centimeters. Remember, you must convert to meters. So if R is 5 centimeters, it is 0.05 meters. Now this is going to work for the magnitude of force 1 and the magnitude of force 3. For the magnitude of force 4, we're going to have to look a little more carefully at the square. We'll do that in a second. I'm going to calculate this one first. So this is 9 times 10 to the exponent 9. Now, I use this notation with my class because this notation goes straight into a computer to calculate. This is not standard notation internationally. However, it's easier to write 9e9 to represent 9 times 10 to the exponent 9. So same thing here. I'm going to write 1e negative 6 to represent 1 times 10 to the exponent negative 6. And if you type that into pretty well any computer system, it's going to interpret it correctly and do the calculation for you. So I've got 9 times 10 to the 9 times 1 times 10 to the negative 6 times 1 times 10 to the negative 6. And that's all divided by 0.05 squared. So I've got 9 times 10 to the 9 times 1 times 10 to the negative 6 times 1 times 10 to the negative 6. And then the whole thing is divided by 0.05 squared. And that gives us 3.6. Okay, so from here, I can update my diagram. I've got my positive charge, and I've got 3.6 newtons forward, and I've got 3.6 newtons to the right. And over here, I have this unknown force F4, and its direction is forward and 45 degrees to the right. Now I want to find the magnitude of force 4. So I've got positive charges. They are all arranged 5 centimeters apart along the points of a 5 centimeter square. I found the force from this charge, and I found the force from that charge. I'm looking for the force on charge 2 coming from this one over here, which I labeled to be charge 4. So I need to know this distance here. Well, if you look closely, we have a right-angled triangle. So via the Pythagorean theorem, r squared is 5 squared plus 5 squared, which is 25 plus 25. It is 50. So r is the square root of 50. Square root of 49 is 7, so the square root of 50 is going to be just over 7. It's 7.07. So to find the magnitude of force 4, that is the magnitude of the force that acts on this charge coming from this charge. You see these charges push apart, and the force with which they push apart. The magnitude of F4 is 9e9, that's K, 9 times 10 to the 9, times Q1, times Q2, over r squared, and r is 0.0707 squared. Remember, convert that to meters. Everything must be in coulombs, meters, for the force to come out in newtons. So I'm just going to go ahead and put this into the calculator. So I've got 9 times 10 to the 9 times 1 times 10 to the negative 6 times 1 times 10 to the negative 6, and the whole thing's divided by 0.0707, and that value is squared. We divide by the square of the distance between the charges, giving us a force of 1.8. So the magnitude of that force is 1.8 newtons. So I'm going to further update my diagram. So on this charge, I've got 3.6 newtons to the right, 3.6 newtons forward, and 1.8 newtons. And that 1.8 newtons is going forward 45 to the right. These are three vectors, and I'm looking for the net force on this charge. All I have to do is add these three vectors. If you do arithmetic, 3.6 plus 1.8 plus 3.6, you're going to quickly get the wrong answer. When you're adding vectors, you got to put these arrows tip to tail, and then do a little bit of trigonometry to sort it out. So when I add these vectors, remember this is force 1, this is force, let me get this right here. That's force 3, and this one is force 4. I'm going to add force 1 to force 3 first, and then I'm going to add the result to force 4. So, force 1 plus force 3. Force 1 is 3.6 newtons forward, and force 3 is 3.6 newtons to the right. So the resulting force, when I put these tip to tail, is going to have a magnitude that's the square root of 3.6 squared plus 3.6 squared. And its direction, you can see the symmetry here. If you're unsure of yourself, the inverse tangent of 3.6 over 3.6 is the inverse tangent of 1, which is 45 degrees. So we've got 3.6 squared plus 3.6 squared, and I'm going to take the square root, and it gives me 5.09. So the magnitude of this force is 5.09 newtons. So now when I add up all of these forces, I've got to add all three of these. F1 plus F2 is going this way with a magnitude of 5.09, and F4 is going in exactly the same direction with a magnitude of 1.8. So this is force 1 plus force 3, and this is force 4. So when I add them all together, now that they're in a straight line, I can do simple arithmetic. When I add them all together, the resulting force, so this is the net force, it's the sum of all three forces, it's 5 plus 1 is 6.89. 6.89 newtons, and the angle is forward 45 degrees to the right. I'm going to do a quick recap, and then I've got to head off to an assembly. So, we've got 4 positive charges. They each have a magnitude of 1 microcoulomb. See, 1 coulomb is a pretty large charge. I'm going to measure these in microcoulombs. 1/1,000,000th of a coulomb. So I've got 4 charges. They're all 1/1,000,000th of a coulomb. They're all arranged 5 centimeters. They're not all 5 centimeters apart. They're all arranged on the corner points of a square that has a length of 5 centimeters. And we've looked very closely at this charge here. We found that this charge will push this way, this charge will push this way, and that charge will push that way. And when we add all those forces together, we end up with a net charge, and our net charge is going this way, and it's got a magnitude of 6.89 newtons. And the angle is clearly forward 45 degrees to the right.